Hello, welcome everybody. My name is Christian Muise, and today I'm going to talk about theory alignment via classical encoding of regular bisimulation. This is work done with a few students that I had the pleasure of working with last semester on their senior undergraduate project. We are from Queen's University, and it was done as part of the Model Understanding Lab here. So let's dive in and sort of pick this title apart. What do we mean by theory alignment and what's actually going on here? Well, the idea is that we're taking state representations, planning models, domain and problem files in PDDL, and we're trying to take a pair of them and align them to see if their state spaces coincide with one another, right? So we've got the two reachable state spaces, and we want to figure out, do they align in some sort of way? Now, the way we're going about this is to lean on a theoretical foundation of regular bisimulation. We don't go deep into the theory for the paper, so don't worry for this talk in the paper. But the idea is fundamentally regular bisimulation, and that means that the states, they might differ in the number of states that you have, but if you look at the action sequences between them, you will find that they align directly, right? So here we have two different state spaces, one with, or both with 3 nodes, but they align because the action sequences and how you move around coincide exactly with one another. And so that's what we're trying to do for this alignment. Then finally, we're using classical encoding for this. And so surprise, surprise, we're taking our 2 domain and problem file pairs and merging them to become a third domain and problem file pair and solutions to that third domain and problem file. And that will give us an indication whether or not the 2 theories align. Okay, so that's the plan for today. But why would we want to do this in the first place, right? Well, it's a good question. One, it's fun. Why not, right? Theory alignment and the different ways you can merge these different things. It creates a nice, rich set of problems to be given to our classical planners, and some of these actually challenge the classical planners quite well. And it takes them a solid few to figure out the solutions. More crucially, I guess, it's a foundation for an interesting suite of techniques here on model alignment and how we can go about finding objects that connect to one another, predicates that connect, and see how 2 different theories kind of can match one another if you view it in different ways. Kind of a PDDL isomorphism, if you will, right? So this is the foundation for that richer idea of research. But most fundamentally, a teacher's got to teach, and we actually use this technique as a core aspect to the marking of a PDDL assignment in a 3rd-year AI class. And so we'll see examples of how this actually played out later on in the presentation. All right, is this KEPS? We would argue yes, and this is a question asked by one of the reviewers. From the KEPS call for papers, domain, model, problem, and plan validation is a core component of KEPS. And what this offers here is, again, a foundation for this advanced domain model validation. If we have a reference model and you're trying to check another model to see if it matches the behavior we would expect for our reference model, then this is what this notion provides for us, right? So this is where it squarely fits in here. Okay, so what is the process for this domain model alignment that we're doing? The first step is that we merge the 2 domain and problem files, assuming that they have exactly the same types, objects, constants, and action schema. Right, and so you are not allowed to have a different set of types. The types can't mean different things. They are the exact same set of types, objects, and constants inside of your problem and domain files respectively. And the action schema here means the action names and the parameters, the typed parameters that are inside of it. We require this because when you're moving around the state spaces, we want move from A to B to mean the same thing in domain 1 as it does for domain 2. So these are the requirements of the assumptions that we have. Notice that we have not stipulated anything about the predicates or the preconditions or the effects. This is what can diverge between the 2 models. Okay, so the next step is we merge the initial states once we rename some of the predicates here. Then we merge each of the actions inside of the 2 domains. We create new actions, divergent ones, and I'll explain what those are in a moment. And then we set the goal to fail. And so the idea here is if you can find a failure, you have a certificate of why these 2 domains do not align with one another, right? If no solution exists, then you know that the state spaces align under the notions of regular bisimulation. Okay, so the example we'll use here is flipping a light switch. This is one of the two domains that anybody would sort of go to when you first see this problem. Here we have just a single predicate on for a light, and the precondition is that it's not on, the effect is that it is on, and turning it off, it just reverses those two things, right? And in the initial state, we have that light 1 is on, and we don't talk about light 2, the other object, because we assume it to be off, right? Which means it's not on. Now, the first step in this is to merge the problem files. The second domain has a predicate for both on and off, and so what you'll see here is we have a prefix for domain 1 where the light 1 is on. Here, for the second domain, we have a prefix for domain 2, and we say light 1 is on and light 2 is off. This comes from the initial state of domain 2, and our goal is to fail. Okay, now let's look at the interesting stuff. What happens when we start merging actions together? This is the turn on action for domain 2. You'll see the precondition is that it's off. The effect is that it's on and not off. Right? The turn on action for domain 1 is that it's not on, and then it becomes on. The way that we merge these two is to take the prefixed predicates that we would be using for the individual domains and creates just a single turn on action that has the preconditions and effects for each of their constituent domains. And so the precondition here for this new sort of merged turn on action is that in domain 1, it is not on. In domain 2, it is off. And the effect is in domain 1, it is on. Domain 2, it is on. And in domain 2, it is not off. Right? So we've taken the preconditions and effects and just taken the union of each of them. And there's no overlap here because we prefix each of those predicate names. Okay. Now, what about these divergent or failure actions? What's happening here is that we want an action for each of the original ones, a pair of actions actually, to say, when you execute this, it means that the original action here, turn on, happens to work in one domain, but not the other. And so if we're turning on here, it happens to work in domain 2, it happens to work in domain 1, but not domain 2. So in domain 1, on is off, right? Or sorry, in domain 1, the on predicate is false. And in domain 2, the off predicate is false. And so that's incorrect here. And so if we can execute this action, it means in domain 1, we could turn the light on, but in domain 2, we could not, right? And so this identifies a place where we have failed to align the two action theories. Similarly, this is how we fail in the opposite direction. If you want to turn it on, in domain 2, it means that it's off. But in domain 1, this is a failed precondition, right? The real precondition was that it was not on here. So these sort of failure actions tell us when you can execute an action in one domain, but that same action does not work for the other, okay? And here's a buggy model. For example, if we were to change domain 2 to have, the precondition that it's off, the effect that it's on, but neglect to include the fact that it should no longer be off, this buggy domain, when merged, will create a solution that looks like this. You first turn on light 2, that works in both of the domains just as you would expect, and then you fail to turn on light 2, which means that you can turn it on again in domain 2, but you cannot do it in domain 1. So we have a failure of alignment here, and we have found a counterexample of where this might have gone wrong. So what are the results for this when we go ahead and try to implement it? We implemented this entire procedure using the Tarski library to create and mangle PDDL. We run it along with Val on the solutions found. I'll describe that in a second. And then the PDDL assignment was given to approximately 86 teams. There's 160 students in a third-year AI class, and the TAs were asked to identify how they found the errors given the analytics that they were provided for this assignment. Just for reference, the assignment was asking you to create a model where you have an agent that picks up colored keys, unlocks doors, gets other keys that have multiple uses or limited uses, right? So it gets the rainbow key, unlocks, gets the treasure. It's your usual maze type of thing with corridors that can collapse keys that have limited use, all of that sort of fun stuff, right? So this was the domain that the students were creating. Now, the problem analysis here looks at a few different things, and this is what the TA would see, the teaching assistant. First is the solve column, and were they able to solve problems 1, 2, and 3 that they had to model themselves? The student validation column says the solutions that they created, do they validate given the reference model that I wrote as an instructor, right? We use val for this. Because we have the same objects and the same action names in the parameter space, we can take their solutions and our models to validate, and vice versa, do our solutions validate on their models. And then we have the alignment columns to see, is there a solution found that proves that they do not align? And you might find that they validate across the solutions all work, but there's something wrong with the theory that doesn't create an incorrect solution when you're solving, but is still incorrect in terms of the model itself. And that's what this alignment process gives us. So the total results here, we had about 86 assignments. Plan-based errors, there was 11 found. This doesn't need to sum total to 86 because submissions had multiple errors. The key thing to look at is 67 of the 86 assignments had errors that existed and were found with this alignment process, and 9 of that 67 had multiple errors found with this alignment process. One example of this is the unlock here, and so the precondition is that a corridor is unlocked and you're going to unlock a particular color. They've got everything right with the keys, and the 2-use becomes a 1-use key and that sort of thing, and the corridor becomes unlocked. That's correct, but what they've missed is to delete the locked predicate from it, right? And so this is the let me erase this stuff here. This is the misalignment plan found for this. You move, you pick up a key, you move, you unlock, and when you unlock a second time, it uses this key a second time when it should not be able to. And so this is how it identifies those very subtle errors inside of these domains. There's a number of possible extensions here. Analyzing the preconditions that might have failed in this alignment is one of them. Another is the goal analysis isn't included at all. Introducing goal achieving actions would accomplish this. So if there's a bug in their goal specification, we would find it as well. Another is plan diversity, generating multiple plans for these alignment failures to indicate different failures inside of the models. And an iterative model refinement, so fix the error that you have found or take that failure action out and see if you can find more errors, because at the moment it just stops at the first error that it finds. So in summary here, we've introduced a new encoding technique for model alignments, based on regular biosimulation. We demonstrated the strength of this as a very, very useful diagnostic tool for grading PDDL assignments, but just aligning two domain theories. And we've identified a number of exciting avenues to sort of take this further. It worked extremely well in this assignment for the AI course. We plan to package it up as a library that you could use off the shelf in your own courses or for your own model alignment. So with that, thank you very much for listening, and I'm happy to take any questions that you might have on model alignment or life in general. Cheers.